Alright, today we're going to be talking about analytical geometry. So, as you might already know, analytical geometry is when you do geometry with lines and shapes on a coordinate grid. As you can tell by the title of this video, this is going to be on the medium level, meaning that I'm going to assume you know basic things such as the different ways of writing the line equation. Alright, so let's get into it. By the way, if you want to look at the prerequisites for this video, I'll put them under this video on the written section. Alright, so let's get started with the formula for the distance between 2 points. So this is probably one of the most important formulas that you can know in analytical geometry, just because, you know, it's just so fundamental to essentially any contest problem that you'll solve. Most of them will require you to use this in some way. So let's get into it. Let's say you have 1 point with coordinates x1, y1, and another point with coordinates x2, y2, and we're trying to find the distance between these 2 points. So the way you'd approach this problem is just a quick derivation of the formula, which you can use is Pythagorean theorem, because you know you can draw a right triangle, and so the distance is the hypotenuse of this right triangle, meaning that by Pythagorean theorem the distance is the square root of the first side, which is the difference in the x coordinates squared, plus the distance in the y coordinates squared. So that's our first formula for this video, right? It's the distance between 2 points on a coordinate plane. Okay, so that's pretty straightforward. Next, let's move into something a bit more exciting, and that's going to be thinking about the slopes of 2 perpendicular lines. So let's draw ourselves a coordinate grid here. All right, there's your x, y, and okay, let me zoom in a bit. Okay, here is our first line, and here is our second line. And these 2 lines are perpendicular. So what we want to derive using this setup is that the slopes of any 2 lines that are perpendicular are negative reciprocals of each other. And if you don't know what that means, we'll get to that in a second. So let's get right into it. How we're going to derive it is, well, first here's the intersection point, right? Let's choose a point on the first line that's, you know, that's about right here. Okay? Now what we can do is draw a right triangle using that distance along this first line. This is line 1, line 2. Using this distance as the hypotenuse. Okay, great. Now, let's do the exact same thing on line 2 with the same length of the hypotenuse. So, you know, just eyeballing it sort of seems to mean that it's about here. Yeah, somewhat. So, you know, if we draw the same right triangle for the second line, this is what we get. And keep in mind, I created these triangles so that this length is equal to this length. So, alright, let's see what's up with these 2 triangles. Well, first of all, they're obviously right triangles, but we can do a bit better than that because we see that they also intersect at a point that's a right angle. And, you know, this is the point, you know, this is a right angle, right? So, okay, let's say in this right triangle, this angle is A and this angle is B. What would this angle be, given that information? Well, because this entire thing is a right angle, it's a right angle, you know, this angle in here would have to be A, just because A plus B equals 90 degrees, right? So given that, you know, you can reason that this is B, and from there, it's quite clear that because they share the same hypotenuse and all three angles are the same, these two triangles are congruent. So from there, we can just set variables to the sides. Let's say that in this case, what looks slightly like the shorter side, let's call it x. Actually, no, that's not good because, we already have x there. So let's just call it r, okay? And, okay, so if that's r, let's call the longer side m. Okay, I'm just choosing random variables right now. So for this inner triangle, that short side in there would be r as well. And for this triangle out here, this length would be m. So I know this is extremely messy and cluttered, but basically what this shows is that these two lines have what looks like a very similar slope, right? Because let's look at line number 1. From here we can see that the slope is, obviously it's a change in y or change in x. In our case, that is r over m, right? And it's good that that is positive because the line has a positive slope. All right, so that's the slope of line 1. What about line 2? So line 2 is this triangle right here. And the slope of that is, we see that the y is your m, change in y is m, and change in x is r, right? So m over r. But we're not quite done because the line is, clearly it has a negative slope, so we have to add on a negative sign in there. So that's the slope of line 2. So now this is interesting, right? Because, we have these two perpendicular lines. The slope of one of them is r over m. For the other one, it's negative m over r. And these are negative reciprocals of each other. So, okay, now you might be asking, if you don't know already, what is a negative reciprocal? Well, if you multiply two negative reciprocals together, you get negative 1. And we can verify this because, the r's cancel out, the m's cancel out, leaving you with negative 1 equals negative 1, right? So a and b are negative reciprocals if they multiply to negative 1. Or in other words, a equals to negative 1 over b. Okay, so this is a very neat result, and as you'll see, it'll come to use when we solve some of our practice problems. Just keep in mind, simple rule, perpendicular lines have negative reciprocal slopes. All right, perfect. So next, let's move on to our last derivation. Rather, let's just, I'm not going to actually derive the formula just because it's going to take a long time and I want to get to the problems. So I will, I'll put the derivation under this video as a written portion, but the formula itself is for the shortest distance rather between a line and a point. So let's say we have a point with coordinates x sub 0, y sub 0, or x naught, y naught, whatever, same thing. And the equation of the line in standard form is ax plus by plus c equals 0. Alright, so the goal is to find this dashed distance, and this would be the shortest distance between the point and the line because, it's at a right angle. And the formula for this is distance equals the absolute value of a times x naught plus b times y naught plus c over the square root a squared plus b squared. Alright, so take a minute to try to just internalize this formula, memorize it, because on a contest, this can be really helpful. It's just literally one quick formula instead of doing a bunch of slopes, line equations, all that stuff. You can just, instead of doing all that, you can just plug it in and get the shortest distance. But for the mathematically curious out there, this might not be satisfying enough. So I will post a proof down below in the written portion. But just to give you a quick overview of how you might approach it, obviously there's the algebraic way where you just find the intersection of two lines and you just chunk through a lot of algebra. But there's also a way to do it using vector projections, which I personally think is pretty neat. And yeah, it involves taking a vector and projecting it with the normal of this line. So anyways, yeah, that's that for this formula. Shortest distance from a point to a line. So now that we're done going through just a brief overview of what analytical geometry is all about, at the medium level, let's work through some problems. All right, let's start with this one. So this is taken from the Euclid 2019. It's question 6b. Okay, just take a minute, read over it, try to pause the video, figure it out on your own, and when you're ready, come back. All right, so the question says, basically, we have these three sides of the trapezoid. They form a geometric sequence. We have to prove that AC is perpendicular to BD. All right. So at first, questions like these might not come off as an analytical geometry problem, but yeah, it just takes a bunch of experience. Eventually, you'll have that sort of gut feeling that, hey, if I put this on a grid, it's going to make my life much simpler. So let's do that here. Also, side note, most of these problems that that I'm going to go over today, they're probably solvable with Euclidean geometry. It's just that analytical is a bit more straightforward, and if you're rushed for time on a contest, you can't really think of a Euclidean geometry solution. It's a pretty surefire, foolproof way to solve a geometry problem. All right, it's kind of like a brute force, but yeah. Okay, so let's do it here. I'm just going to put it on a grid, this trapezoid, and let's think about it. So first of all, the most clear piece of information we have is that the lengths AD, AB, and BC form a geometric sequence in that order. So let's call AB A, okay, lowercase a, this is a random variable. AB would be A times R, and BC would be A times R squared. Clearly A, comma, AR, comma, AR squared are a geometric sequence in that order, right? Okay, perfect. So now let's think. We need to prove that AC is perpendicular to BD. So we need to prove that this angle right here is a right angle. Okay? So, how about, so here's the approach to solving this problem, is to think about the slopes of AC and BD individually. So that's the key insight. So first, let's look for the slope of AC. So the slope is, a change in y or change in x. In our case, change in y is AR. Change in x is AR squared. But because this is the line, it has a negative slope, we need to put in a negative sign in front. All right? So we can simplify, stuff cancels out, and it's just negative 1 over r. That's the slope of AC. Okay, that's perfect. How about we now find the slope of BD? Now I'm going to change to a different color just to, make sure you don't get too confused with all this writing. Okay, what's the slope of this line? Well, change in y or change in x gives us, well, the change in y is AR. Change in x is A, right? I'm just using this right triangle here. Right, so AR over A, and simplifying that cancels out, we get R. So yeah, just you can rewind the video a few seconds if that was a bit too fast, but essentially we're finding the slopes of AC and BD individually in terms of A and R. Fortunately for us, as you saw, the A's cancel out and we're just left with R's. So now this is very interesting. Remember that one of the results that I showed you earlier on is that the slopes of any two perpendicular lines are negative reciprocals of each other, right? And the whole point is we're trying to prove that these two lines are perpendicular to each other. So are their slopes negative reciprocals? And you know, you might be getting excited right now. And let's see. So r times -1 over r, clearly this is -1. So this concludes our proof that AC and BD are perpendicular because their slopes are negative reciprocals of each other. And that is exactly what they wanted us to prove. Okay, perfect. Give ourselves a little check mark there. Let's move on to the next question now. This one is slightly harder, but you know, it's a bit more straightforward. The cool thing about this one is that it tells you that it's on a grid, right? So you don't have to, you know, think to yourself for a second. Hey, should I put this on a grid, or should I approach this using Euclidean geometry? Yeah, they just tell you to put it on a grid, so it's a bit more straightforward. The question is, you know, prove that WA is parallel to KD if MN is half of AW plus DK. So that's a mouthful. But yeah, let's get into it. Essentially, we're trying to prove that this and this are parallel, given that this length is the average of, you know, the top side and the bottom side. Okay, so the average of the lengths of the top side and the bottom side. Okay, that's pretty interesting. Once again, you can probably solve this using Euclidean geometry, and you know, your gut feeling might be telling you that, you know, obviously this is true, because you might remember from a trapezoid that, you know, if the whole point of a trapezoid is that because the two sides are parallel, the middle length is the average of the lengths of the top and bottom sides. Like that's just a result from, you know, it's just a fact of the shape being a trapezoid. But obviously we can't just say, oh, it's a trapezoid, you know, it makes intuitive sense. We can't say that, right? We have to prove mathematically. So let's do it. Okay, so the first step is to set our variables. All right, so how are we gonna do that? Okay, so how about we first set W as A comma B. Okay. We set A as C comma D. And we set D as E comma 0. And, you know, obviously the comma 0 because it's on the x-axis. And now we need to do some brute force. All right, so let's first find M. What is M? Well, M is the midpoint, right, of W and K. They tell us that up here in the question. The midpoint of KW is M. So, you know, from our, you know, the midpoint of 2 points is just the average of their coordinates. So, you know, M is basically just A over 2, comma B over 2. Perfect. What is N? Same thing, it's just the midpoint. So it's C plus E over 2, comma D over 2. All right, so now what we want to do is, they tell us that MN, the length of MN is half the length of half the length of AW plus the length of DK. So let's just find all those lengths. So what's the length of MN? Now you might remember this was also one of the formulas that we just went over, the distance between 2 points, and plugging it into that formula, we get that length MN is A over 2 minus C plus E over 2 squared plus B over 2 minus D over 2 squared. All right, perfect. Next, let's find the length AW. And AW, because you know, in terms of our variables, that length turns out to be A comma B, C comma D, minus C squared plus B minus D squared. Make sure that's right. Yep, that's right. All right. Perfect. And the last thing is dk. And keep in mind, all I'm trying to do here is find the individual lengths of all of these distances in the formula. So dk is, oh, this is convenient. We don't even need the square root. It's literally just e. The length of dk is e because it's parallel to the x-axis. I can erase that off. dk is e. Great. So they tell us that mn is half of aw plus dk. So let's set up that equation. Mn is half of aw plus dk. Okay. Mn is that entire square root thing that I do not want to write again, but all right, I guess I'll have to. Okay. A over 2 minus c plus e over 2. This is not a 9, it's a squared plus b over 2 minus d over 2 squared equals 1/2 square root of aw, which is, you know, a minus c squared plus b minus d squared. Pardon my writing, it's a bit messy. Oh. And then, you know, plus dk, which is conveniently just e, right? So, okay, let me change up colors here because my eyes are... Okay, anyways, here's what we have now. So, at this point you might be like, what on earth is going on? There's like 5 variables. How the heck are we going to prove that WA is parallel to KD? And honestly, what we can do is just try out a bunch of different things, right? Let's just try simplifying this entire thing first. So, let's simplify, yeah. So multiply both sides by 2. All right, 2 square root of all the stuff equals square root of all that stuff plus e. Now what I'm going to do is I'm going to square both sides because I don't like the radicals. And maybe we can simplify it somehow. So squaring the left-hand side, we get 4 times, okay, a over 2 minus c plus e over 2 squared plus b over 2 minus d over 2 squared. Okay. Equals, on the right-hand side, we get a minus c squared plus b minus d squared. Okay, plus 2e square root a minus c squared plus b minus d squared plus e squared. Okay. All right. So now, at this point, you might be seeing something interesting. There does seem to be a way to simplify this, and we can sort of think about it from this perspective. Okay, you see these 2's in the denominator here? Let's see what happens when you factor them out, because, you know, there's a 4 out here in front, so maybe we can do some canceling out, right? So, yeah, this is exciting. Okay, 4 times, let's factor out the 1 over 2, right? So it would be 1 over 2. Okay, actually, I'm not going to skip steps. 1 over 2 times a minus c plus e. Holy, okay. Is this correct? I cannot see. Yes, this is correct, I think, hopefully. Plus, and we factor out the 1 over 2 from the other one as well, from the other term as well. B minus d squared. Okay, make sure this is perfect. Yeah, it looks correct. And, okay, equals whatever we had. Okay, on the right hand side. You can just carry that over. I don't need to rewrite it. And now, this is very, very, very interesting, because look what happens here. Oh, I forgot the bracket here, didn't I? I think so. Okay, basically, this is this stuff. this is that stuff, and the 4 is still, you know, out in front. Okay. So look what happens now that we take this 1 over 2 outside of the brackets of the square, right? Because then it just becomes 1 over 4 times a minus, you know, c minus e squared, and then plus 1 over 4 times b minus d squared. And then you have a 4 out in front. The 4 cancels out with the 1 over 4. And on the left-hand side, we're left with a minus c minus e. Actually, I'm just going to leave it as it was before. Squared. Okay, this is just this form. I'm just going to leave it here. Plus b minus d squared. And now you should be getting really excited because after all this hard work and, you know, algebra, look what we had on the right-hand side. Equals this, right? This stuff in blue here. And there's a very convenient canceling out because we can cancel out the b minus d squared from both sides. So this is very, very good. Let's do some more algebra. Change up the color because, oops, okay. Okay, so let's do some more algebra. A minus c plus e squared equals a minus c squared plus e squared plus 2e. Also, keep in mind, during an actual contest, a problem like this wouldn't take as long as it is for me right now. It's just because I'm trying to explain all my steps, so don't feel too intimidated. It's not actually that much work, you know, for a math contest problem. So, yeah. Anyways, let me make sure I copied it down properly. Yep, seems correct. Alright, so that's correct, okay. Okay, now here is something else that has just popped out to me actually, and I feel like it might make our life much more easy. On the left-hand side, this is not how I initially solved the problem. I'm just thinking of this on the spot, so bear with me if this is wrong. But what if we took the a minus c and separated it from the e? So like that. A minus c in brackets minus e. It's the exact same thing, squared. Actually, I feel like this might work much better than the initial solution I had in mind. Because if we expand this out, what we get is a minus c squared minus 2e a minus c plus e squared. And equals to all of this stuff. Okay, now this is very good because a minus c squared cancels out. E squared cancels out. 2e cancels out. And we're just left with the square roots. Okay, this is honestly really amazing. I did not expect that. I was planning on going down the question in a totally different route. But good thing I caught that. That's pretty cool. So yeah, I guess lesson of the day. You know, feel free to experiment. You know, try random things. Sometimes they might work out. Okay. Anyways, so we square both sides. Left hand side we square. So what do we have initially? We had this, and we're just trying to square that. The negative, we can just ignore it because we're squaring. And on the right hand side, we square that entire expression. And we get this. Okay, basically the square root cancels out. And now here, this cancels out. From here, b minus d equals 0, b equals d. Boom. That is our result. After all of this algebra, we've deduced that b equals d. Now you might be saying, what the heck? Like, how does this have anything to do with the two lines being parallel? Well, notice, what happens if b equals d? Okay. What happens if b equals d? If b equals d, that means w and a are on the same y coordinate. Meaning that this line, WA, is a horizontal line. And guess what? KD is also horizontal. Therefore, WA is parallel to KD. And we are done. Okay, that was good. But let's go through one more question. And this one is, I promise, it's a bit shorter than the other one. It just requires a bit more knowledge. It's especially with trigonometry. So yeah, be prepared to run into some trigonometric identities. So brush up on those before coming to this problem. And yeah, this is the last one I have in mind for today. So let's get it done. Alrighty. Diagonal wy of squared wxyz has slope 2. Determine the sum of the slopes of wx and xy. Alright. Okay. Slope 2. That clearly implies to you analytical geometry. Let's put this boy in a grid. Okay, that's your y-axis. X-axis. And, okay. wy has slope 2. So let me draw it so that, you know, we can have wy have a slope of x2. Wy have a slope of 2. As you can see, you know, this video is getting long, so I'm going to try to end it as quick as possible. Alright, so this is my square. It kind of looks like a rectangle, but yeah. So w, x, y, z. These are the 4 points. And alright, so wy has a slope of 2. So this length right here, they're telling us has a slope of 2. Okay, and they want us to find the sum of the slopes of wx plus xy. So one thing right off the bat, notice the wx, the slope of wx is going to be the slope of yz. So those two are equivalent. Also, the slope of wz is going to be equivalent to the slope of xy. Those two are going to be equivalent. So that's going to be pretty useful for us in solving this problem. So let's get into it. First of all, let's think about some angles. So, Alright, so, 1 second, okay. If we draw a right triangle here, what we get is a right triangle with hypotenuse. Okay, basically, we can set the side length of this square to whatever we want, right? So I'm just going to set it to 1, just because it's easier. Okay, this would work with anything. You could even set it to a variable, like set the side length to s, but that gets extremely nasty, so just set it to whatever you want, right? So if you set it to 1, what happens to the length of this hypotenuse? Well, it would be root 2, right? So now you have a right triangle with hypotenuse root 2, and you have some angle here. So I'm going to call that angle in there. I'm going to call it theta, right? And our first equation, sort of, that we have in our hands is that tangent of theta equals 2. And think about it. The reason for this, the tangent is the opposite over hypotenuse, right? So it's, you know, this length over this length. And that is the definition of slope, which they give us as 2. So tangent of theta is 2. Okay, that's pretty neat. Next, let's think about what this angle is. So I'm going to change colors. What is this angle here? Let's call it alpha. So from the diagram, you can see that alpha is theta minus 45 degrees. Just because, you know, it's a square, so this angle in here is 45. So then alpha would be just the theta, right, minus 45. Okay, great. So now notice, what do they want us to find again? Well, they want us to find the sum of slopes of wx and xy, right? So it suffices to just find the slopes of any one of these side lengths, because from there we can just find the slopes of the other ones. Because remember, they're all at right angles to each other, right? So, and if you don't understand what I mean by that, let's just go along with it. I'm gonna find the slope of wz, and then, you know, you can see, you'll see that from there I can just find the slopes of wx and xy very easily. So let's find the slope of wz. Once again, remember, the definition of slope is opposite or adjacent, or change in y or change in x. So tangent of your alpha, right, equals to the slope of wz, right? So this is what we're looking for, slope of wz. So this is very interesting, because now, we know from here what alpha is, right? Well, at least in terms of theta. So if we plug that in, tangent of theta minus 45 degrees equals what we're looking for. This is our answer. Well, answer as in this is the slope of wz, which is basically our answer. It makes the question trivial from there. But the question remains, how on earth do we find this? Because we don't know what tangent of theta minus 45 is, but we do know what tangent of theta is. Tangent of theta is 2. So here, what comes to the rescue is our trig identities, especially the one that says tangent of a minus b equals tangent of a minus tangent of b over 1 minus tangent of a times tangent of b. And this trigonometric identity is going to make our lives so much easier, because now we can apply it to here and say this is equal to tangent of theta minus tangent of 45 degrees over 1 minus tangent of theta times tangent of 45 degrees. And once again, this entire thing is the slope of wz. Okay? So let's just plug it all in, because we know everything now, right? We know what tangent of theta is. It's just 2. We know what tangent of 45 degrees is. It's just 1. And yeah, we plug it in. Let's see what we get. So after plugging those numbers in, we get 1 over... Oh, my fault. I have misleaded you guys. Sorry about that. At the bottom, it's supposed to be 1 plus tangent of a times tangent of b, not minus. So, yeah, sorry about that if I confused you. And you had a hunch that, no, I think it's a bit wrong. You are right. It is 1 plus tangent of a times tangent of b. Alright, so anyways, plugging in the numbers, you get 1 over... Why did I change colors? Okay. You get 1 over 3. Right? 2 minus 1 on the top, and 1 plus 2 on the bottom. Yep, 1 over 3. Okay. WZ, we have found the slope of WZ, and it's 1 over 3. Okay, so that's this thing right here, this length right here. Notice, they want us to find the sum of this slope and this slope. Okay, so WZ is equivalent, the slope of WZ is equivalent to the slope of XY. So we have already found the slope of XY, right? Because it's just 1 over 3, the same as WZ. So that's the first result that we've gotten. XY is 1 over 3, the slope of it. Okay? I should probably say slope of XY is 1 over 3, just because it's the same as the slope of WZ. Okay? Next, the other thing we need is the slope of WX. So now notice, one of the formulas that we went over at the very beginning of the video is that the slope of two perpendicular lines are negative reciprocals to each other. And, in a square, I'm just going to redraw it because it's getting way too messy now. In a square, this one is perpendicular to this one, so their slopes have to be negative reciprocals. Okay, so, the slope of this one is 1 over 3. And by this one, I'm talking about WZ. Okay, therefore, whatever the slope of this guy is, let's just call it, just random n for now. This has to be at a negative reciprocal with the slope of the other of this other side that I've highlighted in blue. Okay, so let's just use that definition to find that other slope. N times 1 over 3 has to equal -1, right? That's the definition of negative reciprocals. And for there, you get n equals to -3. Boom. So, wow, okay, so take a step back. rewind the video a couple of seconds and just make sure you really understand what I did there. Because we know the slope of WZ and this XW is perpendicular to it, we can use the fact that perpendicular lines have slopes multiplying to -1 because they're negative reciprocals. So if we set the slope of XW to some slope n times 1/3 has to equal -1, therefore n is -3. Therefore, slope of, Wx equals -3. And now all you got to do is add them up. And we definitely deserve a drum roll. This is an extremely long video, but here we have it. 1/3 minus 3 equals -8/3. And we are done.